continuing to watch this live stream, but this is the new portion of class known as I'm going to be teaching you about bending stresses. Normally bending stresses, torsional stresses, normal stresses, shear stresses are stretched out over a few weeks. Yes, this is heavy content. This is kind of hard stuff to jump into. All of you who've taken mechanics and materials recently, you're gonna have to go back and recall some of that material. I cannot sit back and teach you what you've already learned. So this concludes the fun, informative section of this lecture. Please tune in next time for me to hear more soul-crushing things. Alright, so let's talk about bending moment stresses. Or we'll just call them bending stresses. Okay, bending stresses occur when you have moments that are off axis that are acting on a system. Okay, and those moments are not acting on the same axis. It's called a bending moment. Okay, a torsional moment is when you have a moment that is acting on the same axis. So, same. Here, because it's off axis, you can actually draw it in the plane perpendicular to the axis of the moment. But what I'm going to do is I'm going to go ahead, I'm going to go back to that last example I just gave you. Okay, here you've got F1, you got F2, you got F3. Okay, we'll even do, you know what, instead of doing this cross section, let's pick a fun one. Let's pick a really fun one. I'm gonna grab one from the back of the book so that I make sure I have the formula for it. This would normally be the section of class where I ask you how your lives are going. And then when you respond, ignore it. Okay. Awesome. Let's have this be a triangular cross section. Why? Because you know what? I'm feeling whimsical. I just crushed dreams. I feel great. I'm the worst. Anyways. What we'll be doing here now is I'm going to go ahead and say, let's say we know F2 is equal to 3,600 pounds. We know that this distance from here to here is 36 inches. Okay, and then let's say we know this distance from here to here is now 20 inches. Okay, so rather than what I did last time where I gave you the forces and then it would not have made sense with the dimensions I was going to give you, I'm giving you the dimensions. The first thing you have to do is you have to do your free body diagram. You have to figure out what these forces are. We don't know what these externally applied forces are. Remember, when I introduced this a few weeks ago, the steps to figuring out the stress involves doing a system-wide free body diagram first of all. So this is our free body diagram for our system. We don't have to do any changes for it. Once we've done a system-wide free body diagram, now we have to calculate some of the forces in the x direction, which happens to be 0, some of the forces in the y direction, which happens to be, if we call this yx, there's our cross section. Let's go ahead and say this is 1 inch and this is 1 inch. Because why not? It's a right triangle, so that's a 90-degree angle. Okay, so some of the forces in the y direction are F1 is pointed upward, F3 is pointed upward, F2 is pointed downward. Okay, and then we got the sum of our moments. The moments are going to be acting in the z-plane, so I'm going to say some of the moments in the ZZ direction are equal to, well, depending on where you want to start, let's go ahead and say we start from F1, which means you have 0 times F1 because there's 0 distance between where we're calculating the moment and where F1 is applied. A moment can't be applied by an axial force. It requires an off-axis force. So having that right there, it's not going to do anything. You're not going to have a moment. You're going to have a 0 radius multiplied by F1. Okay? Radius to F2, which means that's a negative force. It's pointing into the board. So we'll go ahead and say minus 20 inches times F2. And then we'll say radius to F3. My thumb's pointing out of the board, so that's going to be a positive plus 36 times F3. And then we know that's going to be equal to 0. Okay, so those are the three formulas that we're facing right now. I would say solve this one first because this one only has, well, we don't know what F1 is. We do know what F2 is. We do not know what F3 is. So if we do solve this equation right away, we can figure out what F3 is right off the bat. So here we can take out F1 because that's multiplied by 0. Negative 20 F2 plus 36 F3 equals 0. Bring them on two different sides. 20 F2 equals 36 F3. Well, you divide both sides by 20 and F2 is equal to 1.8 times F3. Okay, or F2 divided by 1.8 equals F2. So this is going to be equal to, we know F2 is equal to 3,600 pounds. So divide this by 1.8 and I believe you get 2,000 pounds. Which is the exact opposite of what I had in the last one. Yes. F3 is equal to 2,000 pounds. So a little bit backwards from what we had last time. Now we can plug that into this equation. Sum of the forces in the y direction equals F1 plus F3 minus F2 equals 0. We do not know this one, we do know this one, we do know this one. So F1 plus 2,000 minus 3,600 equals 0. This becomes negative 1,600. We carry that over to the other side, and F1 equals 1,600 pounds. Okay, so great. Now we know this. We can go ahead and draw the shear diagram. If you really want to, that's fun and everything. Super fantastic. It's amazing. It's good stuff. Choo-choo, shear moments. We don't need to for this because in this one, we know that there is a shear stress generated. We covered in the last video how to calculate that shear stress. In this video, we are calculating how to determine the moment, the bending moment stress at that location, okay? So we're only focusing on shear and bending moments. This all should be a review from mechanics and materials for you. Okay, so we know what these are. I'm gonna go ahead and draw my bending moment diagram. Okay, and then we'll take a small cross section right here at F1. At F1, we got this load, we got this load. Dang, I'm gonna have to draw my shear diagram. That sucks. I'll draw it right here. So we got V. Okay, here with F1 being 1,600 pounds. If we take a small cross section, 1,600, then our shear force that's being carried across this beam the entire way, which I'm going to go ahead and call, well, I'm going to call it V in the y direction. Vy is going to be equal to 1,600 pounds. And according to our sign convention, if we have positive on the left, negative on the right, then it's a positive shear. So this is a positive 1,600 shear. We'll go ahead and draw a positive 1,600, which occurs between F1 and F2. Okay. Last time I started from this direction because we all know there's one outside force and I move this way. This time, you know what? I'm going to have more fun. We can go ahead and say it's 1600 minus 3600. Okay, and then the shear stress that's being carried across here, if I were to draw it downward, which is our shear convention, well, it's 1600 minus 3600 means that this is going to be a negative 2000. V equals negative 2,000 pounds that's being carried across that cross section. Okay, that'll jump down here, negative 2,000. We would have gotten the same thing if we would have gone from the left side using F3, which is what we did in the last video. So this is our shear stress diagram. We have two different free body diagrams that we're dealing with. Okay, one of them is just F1, one of them is F1 and F2. Or you could do just F3 and look at the other side if you really want to. All right, so let me quickly, again, because I never remember the conventions for these signs. I feel like they change every time I look at them. Yes, it means I just really suck at memorizing them. But that's why I have a textbook that tells me whether or not shear or bending moment is positive. Am I sure about it? Not really. But once I look it up, then I'm positive. All right. Positive bending looks like this. Where you have the bottom in tension and the top in compression. Okay. I just felt my career as a comedian died, so the rest of this lecture will have a lot less energy and zero happiness. I will not smile. Anyways, so what we have here is if you integrate this graph with distance, what you end up with is a moment diagram. Okay, integrating a constant value does result in a linear value. If this was a linear increase in shear forces, which may happen over a distributed load, this would be a parabolic value for your moment. Okay, it's just an integral of what's up above with respect to the direction x. Okay, direction you're going across. So integrate that, or we could just sit here and say, all right, this has no moment, but it carries a moment, goes across this cross section. Okay. What you'll see is that this, if I were to apply my right hand rule, this 1,600 pound force, if I'm analyzing it from this location, the 1,600 pound force applies a negative moment. So in order to counteract that, I do have to apply a positive moment here so that it's a negative moment on this side and a positive moment on this side. This is positive bending. Okay, so we're experiencing a positive moment here, and what we're dealing with the positive moment is the further away from the 1,600 pounds we get, the bigger the moment is going to be. Because remember, it's distance times force. Well, the further away you get, the bigger the distance is. Well, the force stays the same, so the moment gets bigger because the distance is increasing. So what you see is that it increases. Now it reaches a maximum moment value at the very center at F2. For this segment between F1 and F2, the maximum occurs at F2. At F1, it is 0. If this distance, when we take that cross section, is 0, there's no moment generated by it. So it starts at 0. On the other side, we have 20 inches multiplied by F1. 20 inches times 1,600 is 3,200 pound inches. 32,000. Okay. Now, if you keep going beyond that, now we have two sources of a moment. Okay. You have a moment that's generated by this. You have a moment that's generated by this. Okay. The equation for this moment is going to be, so here we got this moment. Moment is going to be, let's say that x is the distance from 0 to wherever we cut our cross section. Okay, so we have 1600 times x. That is the moment that is created by this. Oh, I should just do the sum of the moments. I'll do this right. Sum of the moments in the z to z direction for this cross section is equal to negative 1600 times x, because the moment that's generated here is a negative moment, plus m, because we're going to assume m is positive, plus the moment generated by this 3,600 pound force is also positive. The distance from where we calculated on the end to where the 3,600 is pointed in that direction, the thumb comes out. This is a positive moment that's created by this. So the distance, though, is 3,600 times x minus 20. Okay, because we have this minus 20 distance that is acting there. Okay, and we know that this is equal to 0. So if you were to solve this equation, we got minus 1600x, we got 3,600 times x. These two ended up canceling out, and you get 2,000x. 3,600 times 20. So that's 2,000x minus 32,000 plus m equals 0. So here, m is equal to 32,000 minus 2,000x. Okay, as we continue to go along this beam. So you can see when x is equal to 20, yes, when x is equal to 20, what ends up happening is this ends up being 32. Oh, I forgot to multiply that. Nope, never mind. When x is equal to 20 inches, what you get is you get the 32,000 pounds. I don't know why my math isn't saying that. I did something wrong. But at x equals 20, you should see a moment value of 32,000 pounds. It's troubling. And what you get is at 3,600, at 36 inches, when x equals 36 inches, you should see oh no, sorry, this is 72,000. Okay, 3,600 times 20 is 72,000. That's where I went wrong. Whew, okay, so this is 72,000 minus 2,000x. So at x equals 20, you end up with 32,000 pound inches of moment, and then that continues to 0, whereas the 0 location occurs at 36 inches. Okay, so this is the moment diagram that we have. Now to calculate the bending stresses that are caused by this bending moment diagram, you know what? We know that bending stress over here is going to be 0, bending stress over here is going to be 0, and bending stress in the middle, well, really 20 inches in, is going to be caused by this massive bending moment. Since our geometry is identical across here, just looking at this bending moment diagram says, well, that's going to be your maximum bending moment right there, because the geometry is all the same. You got different bending moment. Let's go ahead and calculate the maximum bending stress at this location. So your sigma x, because it is a sigma, and I'm not going to say max because I'm just going to say sigma bending, which is going to occur in the x direction. It is an x directional phase, because remember, when we push down on this, this is going to be pushed down. This top part is going to be put in compression, and this bottom part is going to be put in tension. Okay, compression that's a normal force. Tension is also a normal force. So what we're seeing here is the bending moment is creating tensile and compressive stresses that are normal in the x direction here. Okay, so sigma bending in the x direction is equal to the bending moment occurring in the ZZ direction times y over IXX. Okay, so what this is it's the moments in the z direction, the bending moment in the z direction, the distance from the centroid to wherever that's located, divided by the it's the polar moment of inertia of that cross section. Okay, if we were to have two different bending moments here, it would cause a different interface entirely. That is part of your reading assignment. We're not going to be able to cover that in class today because, quite frankly, we could talk about this for multiple hours, just multitudes of hours. I'd rather not do that. So, knowing this, I'm going to go back and jump back to my table that shows that triangular cross section, because I need to know what the value of IXX is. So just looking at this, I've got my B, I've got my H. According to this value, IX is, so this is equal to, okay, I know what MZZ is. It's 32,000 pounds right here. Y, well, what Y is we could either calculate it up here or down here. The problem with figuring out Y is measured from the centroid. Okay, so the centroid of this shape is about right here. It's actually located at 1/3 of this base distance and 1/3 of this height distance. Okay, so 1/3 of this and 1/3 of this, well, they're both 1 inch. It's located at 1/3, 1/3. The coordinates of this are 1/3 inch, 1/3 inch. So that's fun. But that's all according to what I'm reading in the book right here. Okay, it says there's where your centroid is. It's located at 1/3, 1/3. We know what our B and H are. IX is BH cubed over 36. Now the maximum Y value for this Y value is larger than this Y value. We're going to be seeing a higher stress at the top of the beam than we are at the bottom. Why? Because of the shape of that beam. If this was a rectangle, the centroid, the centroid is right in the middle of that rectangle. Your Y distance from here to here is the same as from here to here. You're going to see identical compressive and tensile loads on the top and bottom. Because this Y distance is only located 1/3 of the distance up, your stress on the top is actually going to be twice as large as the stress on the bottom. That's just because we're using a triangle where the centroid is not in the middle vertically. And I can say that again. You can rewind the video if you need me to. Feel free to ask questions. So what I'm going to do is I am not going to take into consideration the bottom here. I'm only going to take into consideration the top. The distance from the centroid to the top is 2/3 of an inch. Okay, so I'm going to put 2/3 of an inch in for Y. Now I know that Y on the top, I know that that's going to be in compression. Okay, so we got MZZ, which is 32,000 times 2/3 of an inch divided by, and IX for this is BH cubed, so 1 times 1 cubed divided by 36. Okay, so if I run the math on this, I should get a nice number. 32,000 times 2/3 divided by 1 times 1 divided by 36 is going to be equal to 768 1,000 psi. Now that is a massive amount of force. It would probably cause failure in this component. In order to be able to handle this, we should increase the size of our triangular cross section. Just if it has to be a triangle. Otherwise, what we could do is you could use about the same amount of material, and you could just use an I-beam. An I-beam has a different IX value. You can actually look up all the IX values for I-beams online. I don't know if they're provided in this book or not. I'd have to look, but that would reduce the stress. Changing the geometry will change the stress. I haven't even looked at material yet. You can get materials that can handle this amount of force. Yes, but they're very expensive. So rather than that, I would suggest changing the geometry first, if you can. Okay, so that is where this is. If we were to graph the stress caused by the bending moment throughout the entire shape, what we would see is that the graph of sigma bending in the x direction ends up mimicking this graph right here. Okay, it goes from 0, it peaks right there at 20 inches, it goes back down to 0. Where this value right here is 768,000. So these two graphs have the same shape, just the same way that the shear force and the shear stress graphs had the same shape. Okay, so that's bending stresses. Now we're going to cover torsional stresses. And this should all be a review again from Mechanics and Materials, because we did cover all of this material once already. So, a torsional stress. This is caused by a moment that is on axis with each other. Okay? So again, if I twist this, the moments created on both sides of the marker travel through an axis that is in the center of this marker. Now we are only going to be dealing with circular shapes in torsion, because any other shape in torsion ends up producing a very weird, very complex math equation, which quite frankly, do it in SolidWorks. If you're going to have a torsion like that, do it in SolidWorks. This book doesn't even have those formulas. This book has a lot of very complex formulas. So what you have here is, in torsion, we'll say we have a totally circular bar here, not hollow. Both ends, we have something like this, like that, just drawn out, okay? What we're doing is we're rotating it so that this end is at a slightly different angle. If we were to track a common line across the bar, that common line would curve around the bar a little bit. Okay, when we release the torsion, that line would then go straight again. If any of you have ever installed a garage door spring, you have to rotate, you have to torque that spring until the black line on the spring, or whatever color line on the spring, rotates a certain number of times, and that tells you how many rotations of the spring you have. Okay, so what we're going to do here is, for this time, I'm going to introduce what happens when you have a different geometry here. So far we've been dealing with constant geometries. What's going to happen if I have a shaft like this that gets bigger and then gets smaller again? Okay, this is not uncommon for a vehicle shaft. It's not uncommon for a lot of different kinds of shafts. Allows you to put in bearings and have the bearings go right up next to this big section. It provides a nice insertion point. You basically only have to pin one end of it and have a gear or something on both sides if you need to. It just makes for the entire mechanism to work nicer when you have that step in the middle. Okay. But it does make the math a little different. So here, let's say we are applying a torsional load on both sides of this stepped shaft. And the dimensions of the shaft from the side view look like this. Looks like meat. We'll say that the diameter 1 is going to be equal to 1 inch and diameter 2 is equal to 2 inches. Okay, and we're applying that torsional load on both ends. Okay, and we can say this is 4 inches, this is 4 inches, and this is 4 inches. Okay. Now, ooh, and yep, we're good. Now, what we're dealing with when it comes to torsional stresses, I'm pulling up the formula real quick. You'd think I'd have these memorized, but I do not. Okay, the formula for torsion is tau is equal to torsion times the radius divided by J, which J is the polar second moment area. Okay, so what direction is the shear stress generated by torsion? Well, this is kind of hard, because if we draw a circle here, the shear stress is being generated on a plane, which if this is the y-x plane, if we look at it so that this is in the x plane, which in the x plane you see y and z, you don't see any x. Kind of the interesting thing about it, I discussed that in the last lecture. In this plane, at this location, you're going to have a y-facing force, shear force. At this location, you're going to have a z-facing force. At this location, you're going to have a y-facing force. At this location, it's going to point in both the y and z directions. So that's interesting. The location of where you are measuring the stress dictates whether or not the stress is in the y direction, the z direction, or in both the y and z directions on the x plane. So that's kind of ugly. But that said, if we only analyze stress at one location, say we just look up here, where there is only a z-facing stress, or we only look over here, where there's only a y-facing stress, then all we're dealing with is tau yx. Okay, so this is a tau yx, or up here this is a tau zx, or tau xz, which are the same values. That's it. We're not dealing with any other stresses. So you can still find a planar stress condition if you only look at one location on the shaft. Like for example, if this is in torsion and there's a bending moment such that you have a force bending stress that occurs in the x direction across all of here, but you also have a shear force that occurs in the y direction, then you're probably going to want to take the calculation right here if you can. If you can't, then you have to go up here, then it's no longer a plane stress. Having a tau zx means you're not dealing with plane stresses anymore. Anyways, plane stress discussion aside, this is the formula for tau. This could be tau xy or tau xz. And this is equal to t, which is in the xx direction. It's the moment in the x direction. This is a moment in the x direction, times rho, which is either going to be in the z direction or the y direction, here. So this is rho z or rho y. If it's rho z, then it's this, because that's the distance in the z direction from the center. If it's rho y, then it's this one, goes here, because it's the distance from the center to that location in the y direction. Okay, and here, J, this is second polar moment. I believe this is xx. So if I go back and I look up my formula for what J is equal to pi d to the fourth over 32. So I can just plug all this in. Let's say we're going to figure it out. We're going to figure out tau yx, which is located along this plane right here. Tau yx, tau xy is equal to, we've got our, oh, I didn't ever say what t was. Let's say t is equal to 1,800 pound-inches. Okay, and that's going to equal 1,800 times our rho is the distance from the center to where we're calculating the stress. It's going to be a maximum at the outside of the shaft, because when rho increases, that stress is going to increase. So we'll go all the way to the outside of the shaft, which is going to be ½ an inch away, and divide that by, it's d to the fourth, pi d to the fourth over 64. Okay, where d here is 1 inch. That's what we said right there. Okay, so running that awesome maths. Pi times 1 4th 64. And what you have is, this is equal to 18,335 psi shear stress located at this edge right here facing you at this location. Now the geometry and the torsional load does not change from here to here, so that stress is constant from there to there. However, the geometry changes here and it's different here. So while this tau max is equal to 18,335 psi, this is different. We're now dealing with a much larger shaft. Okay, so let's do the same thing. Tau xy is equal to, we're applying 1,800 pounds. Here, at this point in the shaft, this is 1 inch because this is a 2-inch diameter shaft. The radius is 1 inch. So 1,800 times 1 divided by pi d4 over 64. Where here now, d is 2 inches. When I plug this in, and I calculate it, doop-a-doo, boop-a-doop. This stress is now 2292 psi. Okay, so this tau max, I'll write it underneath, is now almost an order of magnitude smaller